Okay. Okay, that was easy. I wasn't expecting it to be that easy. And the other thing I can say that I can apologize for a little bit is normally I probably would bring some demonstrations, but the demonstrations are in Manitoba. So I've got a couple magnets and some stuff I can pick up. And we'll use that. So let's see, begin the show. View. So here's the topic. I guess Nina decided I'm Professor Magneto or Magneto or and here's the image that she found, I guess. Yeah. He's wearing a lab coat, so I'll accept that. So the first thing that I guess I want to get across is, why the heck are you even listening to me? So here is quickly, who am I? You heard that kind of stuff. I went to University of Victoria in Alberta. I worked in the US National Lab in the German system for a few years. But the most interesting thing, I think, that I found this by accident, if you look up the Wikipedia page for magnetostatics, here it is. We look at the references. Reference number 1. That's me. There are only 4 references, and the other 3, I make it seem like it's a mistake that I should be there. I should even be there. The Feynman lectures on physics. Richard Feynman won the Nobel Prize, and I have those books at home. And David Jackson's Classical Electrodynamics. I use that book as a textbook, and I have it at home as well. And Aharoni, Introduction to Theory of Ferromagnetism. I use that as a textbook. Technically, I guess I have that in Manitoba. I don't have that at home. And then there's this other one that the way I found this was I was going to be teaching this subject in a class, and I wanted to look up to make sure I had it right, and ran across my name. Yeah. So anyway, here we are. Here's what I want to talk about. First, I guess most of the time I want to talk about the phenomenology of magnetism. By phenomenology, I mean I'm not going to try to explain on the atomic level what's causing magnetism. I probably could, but that's a higher level of talk. We're down here. Sure. Yeah. Sure. Yeah. And so by phenomenology, I mean we're going to accept that magnetism exists. It's a force. What does it do? And not necessarily try to explain it on an atomic level. That's more difficult. So I want to show a basic introduction to magnetism and some magnetic effects, which are interesting and which have some value to explaining some of what people think might be going on in some of these woo magnetic systems. And I'm going to try to relate it to the fields of electricity and light and optics. And then when we've got this background, we can look at the science and pseudoscience of some of the magneto-related claims. So I have here a couple pictures of magnets, but we'll go here. The first thing that you notice about magnets, all the magnets that we know about are dipolar. Dipolar means they have one side, we could call it a plus, and the other side minus. That's not how we do. We call them north and south poles. But there's really, the reason for that we call them north and south poles, is because the north pole of the magnet attracts the Earth's north pole, and the south pole of the magnet attracts the Earth's south pole. And that gives us the idea of a compass. That your magnet inside the compass, if it's free to rotate, should be pointing at the North Pole. So we have these magnets, a bar magnet. One end will point north if it's free to point north. The other end will point south if it's free to point south. I can take my magnet and I can turn it around and make it a horseshoe. And then I've got the north and the south poles on both ends. And here, so with the magnets that I brought, you'll possibly have to trust me, but you can think of this as being a really short bar. That one end's the North Pole, one end's the South Pole. I have no idea which is which right now. And these were technically, these were magnets that I had as a kid when I was playing with them, and they became refrigerator magnets in my house. And so here they are. So here's the experiment that if this was sort of my lab, I would have set up, but I don't know about doing it in the pub. We will take a magnet and hang it from the ceiling. The North Pole should point north, and the South Pole should point south, assuming that everything it's free enough to rotate and there's no other bigger magnetic field than the Earth's magnetic field around. That's a compass, sort of a homemade compass. And then we can think about that. We can say that with magnets, like charges, so two North Poles will repel. Two South Poles will repel. Opposite charges will attract. A North Pole attracts a South Pole. And so what that means then is since the Earth is attracting one pole of the magnets, the Earth must be a magnet. But there's some mistake in all of this. If the North Pole of a magnet is attracted to the Earth's North Pole, those are like charges attracting. So the Earth's North Pole is actually a south magnetic pole. And the Earth's south pole is actually a north magnetic pole. I've told students that what we should do is we should walk over to the geography department and tell them to relabel their maps. And they already think physics is weird, so they wouldn't be surprised. And so here is Earth. It's got a bar magnet in it, essentially. And the South Pole is pointing north, and the North Pole is pointing south. And you might notice if you look a little bit carefully, the North Geographic Pole and then the South Pole or the North Magnetic Pole or whatever you want to call it, they're not at quite the same place, but they're close enough. Unless we really want to explore the Arctic, our compass will work pretty well. Sure.
If you cut a magnet, will it automatically diffuse?
Yes. If I break a magnet in half, I'll have two magnets that have north and south poles, and on both of them, there'll be both weaker magnets than the original magnet. In fact, if you go far enough, you can keep cutting it and cutting it and cutting it until you have only one electron. It still has a north and a south pole to it. So yeah, that's actually one. I have a magnet that I've cut in half and done that with the students, but I don't have it here. So the Earth's magnetic field actually switches direction over time. And this is looking back on some point in the Canadian Shield. So there's some of the older rocks on Earth, and the black means that it's in the current position where the south magnetic pole is north, and the white means it's reversed. And we can see this by looking at the rocks, dating the rocks and looking back, that we can see that the Earth's magnetic field has switched directions multiple times. This axis here is basically a million years, so 5 million years gets us back to here. And the first thing you can see looking at this is the largest time it's been pointing in the same direction in at least the 5 million years that we can find rocks to support in the Canadian Shield is right now. It's the one that we're in. So we're overdue for a magnetic switch. Yes. We will get to the idea of how a current can produce a magnetic field And basically, as the Earth is spinning, there are charged particles in the Earth, and it's going to be producing a magnetic field depending on which way the current is going, either toward the north or toward the south. Yeah.
How long does the switch take? Days, weeks, months, years?
Good question. And the answer, the first answer is we've never been alive when one's happened. We can simulate it, and we think we know how it works. And most likely, you have the situation that the magnetic field is pointing north, and it slowly rotates toward the south, in which case it could take hundreds, maybe even 1,000 years to make the switch. That said, there is another mode that might exist where the Earth's magnetic field basically zeroes itself out and reappears in the other direction. And that could be a matter of a few days. If that happens, I think they believe it probably goes the other way where it slowly rotates, but it's possible.
In that time, if I remember rightly, are we going to get bombarded with radiation from space?
If the Earth's magnetic field zeroes out and reappears, yes. During the time that it's zeroed out, yes.
Which causes all kinds of
Cancers and things like that, yes. Yeah. Yeah. But if as long as the magnetic field continues to exist when it's switching, it'll be enough to deflect a lot of the magnetic particles. But we can see that we're overdue for a switch. And there's actually some reason to believe maybe we're into the early part of a switch, and that's the fact that the poles don't quite line up right now. So it might be in the beginning part of that. But the other thing, if you look carefully at this, the magnetic pole that's in the north, the south pole, is in Canada right now.
It's been studied like it's for centuries now. It slowly progresses, goes a few kilometers here and there.
Yeah.
In the last couple of decades, it's picked up so much more than it ever has in its recorded history. And it's out in the Arctic now. Yeah. Out in the Arctic Ocean now.
Okay.
And it's weakening and it's flying faster than it's ever been.
So maybe.
Maybe we're in the middle of it now.
Yeah. It's hard to say if it's going to take hundreds of years and we're at the beginning of it. Is it really happening or not? Yeah.
It's a complex system.
Yeah. So, anybody who's done some chemistry might be familiar with the periodic table. This is just all the elements that exist, and I want to talk about what exists in terms of magnetic materials. The purple are the interesting ones. The iron, cobalt, and nickel are the most common magnetic materials that we have, and you can make alloys and compounds with them. And then there's also the light purple down here. These are the rare earths, which you may or may not have heard about. Donald Trump wants to make sure the United States has rare earths because they're magnetic. And because they tend to be found in old rock settlements, like the Canadian Shield, there are also some in the Ukraine. So there's another country that he's trying to figure out how to get them from. And China and yes. Not in Panama. No.
DRC.
Yes.
There are lots of them here.
Yes. And so they're light purple because the word we have is they're ferromagnetic. That means that they can maintain a magnetic field when they're not inside a magnetic field, such as my magnets here. These would be rare earth magnets, because the rare earth magnets, you make yourself, the reason they're light purple on here is that at room temperature, they're no longer ferromagnetic. But if you make the right alloy or compound, you can get past that. And at room temperature, they are ferromagnetic. And the big difference between them is what we call soft magnetic materials and hard magnetic materials. Soft magnetic materials, iron, cobalt, nickel, if you magnetize them, and then you take them out of the magnetic field, they will lose their magnetization, depending on what you do, in a matter of seconds, if not less than a second. So, for example, I can say my paper clip is probably nickel. I've magnetized it, and it's now stuck to my magnet. I take it away from it, and I get another paper clip. They're not going to stick together. So it's lost its magnetization. But the rare earths here, the hard magnetic materials, gadolinium, dysprosium, holmium, europium, they will maintain magnetic fields when you remove them from a magnetic field, depending on what you do, thousands or even millions of years. So that's what we call them, permanent magnets. They're not really permanent because they'll only last for thousands or millions of years, but they're good in that if I'm teaching a class, I do a demonstration with a magnet, I put it on the shelf, but I come back next year and it's still a magnet. And that's not going to happen if it's an iron, cobalt, or nickel. And if we want to fill in the rest of this table, the yellow they call paramagnetic, this blue they call diamagnetic. Paramagnetic means that it will feel a weak force in the direction of the magnetic field. Diamagnetic means it'll feel a weak force in the opposite direction away from the magnetic field. And then there's this one here that's red. Chromium. Chromium is what they call antiferromagnetic. Ferromagnetic means that all the spins of all the electrons will tend to line up in the same direction. Antiferromagnetic means there's one spin up, the one beside it's down, and up and down. There's zero net magnetic field, but it's still got some uses in terms of technology. So these are the materials that we have, and the basic idea is we have hard materials. Those are if you went to a science store and bought a magnet. If you wanted to build something for the military that had a magnet in it, you want to make it out of a hard material. So Donald Trump wants these rare earths. And then the next concept we can have is the magnetic field, magnetic fields, and we can draw in magnetic field lines. The idea of a magnetic field line is that it's going to show the direction of the magnetic field in all places. And we've chosen, it's a choice, that in order to give us a direction, the magnetic field goes from north to south. We could have chosen the opposite direction. The reason we didn't is something that I'm going to try to show you later. It's so that we can have what we call a right-handed coordinate system, and this is important if you ever take upper-level calculus classes. It makes life a little bit easier to have a right-handed coordinate system. And what that means is we can actually figure out some directions using my right hand. And so if we have our magnetic field diagram going from north to, well, we have a bar magnet. Magnetic field lines are going from north to south. They never cross one another. If they crossed, what would that mean? That would mean that the magnetic field direction's in two different directions at the same place, and that just doesn't make sense. And if we zoomed out far enough, all of these lines should connect over to the other side because the North Pole is equal and opposite to the South Pole. And then we can look at a bar magnet where most of the lines are going to be coming down between the north and the south. There are some that will take the long route around that are cut off a little. I'm not worrying too much about the numbers or anything, but where you have the most lines close to one another, that's where you have the largest magnetic field. And way out here, it's a smaller magnetic field. You can, the one thing that you can do is sort of, if I had a free north magnetic pole, which doesn't exist. But if I had it, which way would it want to go? That's the direction of the magnetic field. Now, a couple more complicated magnetic fields. We can get 2-bar magnets, and if I place them side by side, if I have the North Pole attracting the South Pole of the other one, we see that there's attraction between them. And if we switch them so that north and north or south and south are pointing at each other and they should be repelling one another, there are no magnetic field lines right in the middle because they're repelling from one another. It says there's zero magnetic field at some point in the middle. Here's the experiment that I really would be scared to do here because I'd be breaking some of the things. If you want to to experimentally see the magnetic field lines, you get a salt shaker full of iron filings and just sprinkle it over your magnet, and they will tend to follow the magnetic field lines. The iron filings don't come with arrows, so you have to imagine the direction, or we can use a compass to figure out what the directions are. There are a couple compasses in the top part of the picture.
So is it like discrete lines that exist with space between them?
There is space between them, and the reason there's space between them is that this iron is going to repel that iron.
So it depends on the strength.
It would,
The strength of the magnet.
yeah. It would depend on the strength of the magnet, and then the iron is magnetized because it's in the proximity of the magnet. And so the problem with trying to do that here is I don't want to get little magnets, little iron filings in my computer and in whatever the overhead is. When I do this with a class, I get one of the old overhead projectors and do it on top of it so there's nothing to break. The other way we can get a magnetic field is we can have a current. An electrical current is a source of a magnetic field. And so if the current is going, in this case the current's going up, there are lines of magnetic field, circles of magnetic field around it. And as far as, this is known as Ampere's law, Andre Marie Ampere, who the unit for current in electricity is named after him. Without worrying too much about numbers, the magnetic field is some constant times the electrical current in the wire divided by the distance you get from the wire. So what that means is really close to the wire, I have a big magnetic field. It drops off with distance. If I put more current in it, I have more magnetic field. And because we have, and so this picture here is showing that on one side of the wire, the magnetic field is coming out of the plane, coming out of the picture. And on the other side, it's going in because it's going around in a circle. And we actually have, because we chose to use a right-handed coordinate system, we have a right-hand rule that we can use. If I point my thumb in the direction of the current, my fingers will wrap around in the direction of the magnetic field. And so the fun thing that you can do with this is when you get students writing their final exam, a lot of times they get put in the gym with about 3 other classes, and the class beside them is a business class or something that knows absolutely nothing about what we're doing, and they're wondering why everyone in the class is doing this. What's wrong? You actually see which students don't care and they're just doing it, and other ones are sort of hiding it.
That's DC current.
That's DC. If it was an AC current, then the magnetic field would be going this way, and then it would be going that way when every time it switches. The field would go. And that's really kind of the explanation for why the Earth's magnetic field switches, that you've got a current that's, because of the spinning, is either going from north to south or south to north, because the Earth's spinning. So,
You said that chrome doesn't magnetize.
well, it's antiferromagnetic chromium.
So when people want to put chrome in their bumper, they put it in a solution and then put electrical current in it.
That's just electroplating it. That's not got anything to do with its magnetic properties.
Okay.
But it actually is useful in that you can pin a material so it has a certain magnetic field if you put it on a layer of chromium, because the chrome will hold it in that way depending on the atomic spacings relative to the other material. So what that means is we can make an electromagnet. And here's a picture of the idea. We're going to make a coil of wire. It doesn't have to be a magnetic material. It can be copper or anything. And we're going to put current through it. And if we want to make the magnetic field large, put an iron core in there, because the iron's then going to be magnetized in the same direction that the current is magnetizing it. And then when we turn it off in a second or so, the current stopped and the magnetization of the iron has gone away, and it's not a magnet anymore. Now, if you really wanted to make a good magnet, you put a huge current and have a whole bunch of coils wound, thousands of coils wound around. And with a huge current, you want to cool it with water, with liquid nitrogen, with liquid helium maybe. So, but here's one that you could make on your own. It's not too complicated. We're going to wind a wire, put an iron nail inside of it, and we want a current flowing, so just attach it to a battery. And this is going to be an electromagnet. And you can even see in the bottom that there's some sort of nail here that's being attracted in the direction. So these are the largest magnetic fields that at least man can make with an electromagnet. And then the next sort of strange thing I want to talk about is the Lorentz force, named after Henrik Lorentz. And we get a force that exists between a magnetic field and a charge that's moving. So if an electrical charge that's moving and a magnetic field, I get a force that's going on. And again, we have a right-hand rule, which I hold my hand like this. My pointer finger would be in the direction that a positive charge would be moving. If it turned out I had a negative charge, well, the negative charge is moving that way, so I'd have to turn it around, or I could, if I really wanted to, I can say I'm going to use my left hand if it's a negative charge, and because it works, because my hands are mirrored. My middle finger is the direction of the magnetic field, then my thumb will be the direction of the force. And so, I mean, this is the way it's generally taught in textbooks. I can tell you I've actually gotten in trouble for this. I was walking down the street in Edmonton when I was working on my PhD, trying to figure something out, and I believe I did that to the driver that was going by. This guy actually stopped his car, got out, and started yelling at me, and I just got out of there and didn't pay any attention to him, and figured out when I was a couple blocks away, I think that's why he was mad at me. I think he thinks I gave him the finger. So I sometimes tell people that maybe this is a good way to do the right-hand rule. But so anyway, in physics, in magnetism, we flash gang signs when we're... So this is actually the first reason why they say magnetism is difficult, that you're going to get a force in a direction that you don't expect. And as a couple examples, here we have a proton, which is positively charged, moving upwards. So my pointer finger says a positively charged object is moving upwards. The magnetic field pointing north. So north is behind me. That means we're going to have a force off to the west. So my proton's going up here and it's being deflected westward by the magnetic field, which is not the direction you would be expecting. Why would you expect that something moving up in a magnetic field north should go west? That's just weird. But that is what it is. So the next example I wanted to say is we have an electron. I changed the coordinates from north and south to say the electron's moving into the board. That means positive charge is coming out of the board. And the positive charge, so I'm pointing my finger out of the board. And we have a magnetic field up. Then the force is, I guess again, in this direction toward the west. But why would you expect that? Now, here's the sort of more complicated sort of final case to try to figure this out. We have a positive charge here, and it's moving up. But we have a magnetic field on some weird tilted angle toward it. Well, I can't figure out how to get my fingers for the part where the magnetic field is given the letter B for reasons of German. And V is the velocity of the particle. But so I can't figure out how to get the magnetic field and the finger and the charge velocity finger to be in the same direction. But that's okay. There's also some component. So the part that's in the same direction isn't causing a force at all. But there's some component that is perpendicular that we can actually use so that it's going up. There's a force that way. So into the board, we're going to be having the force from this magnetic field because there's some angle between them. And we can actually calculate numbers for this, but we're not going to here. We can at least see that the biggest things you can see about this is that the directions are kind of unpredictable with your sort of general common sense. That why should it be in some weird direction? But at least as far as those of us in magnetism, it's completely normal to be sitting there trying to figure something out, and it's like, what's wrong with you when you see you doing it? Yeah. So the next concept I want to introduce is the idea of flux. Now, flux is the amount of a field. The word we use is a vector. Vector just means something that has a direction as well as a magnitude to it that's going through some surface. So if we look at these green pictures, this one where the surface is perpendicular to whatever the vector is will have more flux than this one that's tilted. And examples that you're familiar with, it's a hot day, you want to cool down, you get in front of the fan. You stand directly in front of the fan. You don't stand beside the fan because that's not going to get you nearly as much wind coming off the fan. So you want to maximize the flux by standing directly in front of it. And then the important example for at least our seasons, I've never figured out why the sun's smaller than the Earth in this picture, but it is. Okay. So the Earth is tilted relative to the sun, and in this picture, it's the southern hemisphere that's getting most flux out of the sun. So it's summer in the southern hemisphere, and up here in Kelowna, which is sitting around the backside, it's winter. And then it will switch direction when Earth gets around to the other side of the sun 6 months later. And so these are examples of flux that you're kind of used to. Yes.
And as far as the distance from the sun, that long
Yeah, we're actually a little closer in the winter.
To the sun in winter.
Yes, we are, but we're tilted away from it. So the idea that includes flux that I want to include is something called Faraday's law. And Faraday's law says that if we change the magnetic flux with time, it will generate an electric voltage and therefore current through a loop. So I get my magnet, and if I stick it into the loop, pull it out, stick it in and pull it out, and I do this in some controlled way, I can get an alternating current voltage that I'm producing. And so if we look at these pictures, we have our bar magnet, we're sticking it in, we're going to get, the way this is aligned, a positive current. And then we pull it out, we get a negative current. And if we turn our magnet around, so we're sticking the south pole in, that's the same as pulling the north pole out. So we still get a negative current. And if we pull the south pole out, that's like pushing the north pole in, and we get a positive current. But if the magnet's stationary, we get no current at all. And so this leads to sort of I think it's the most important technological thing that exists in our world today, is generating electricity. And so here's a simple picture of how we're doing this. We have a magnetic field. We have, in this picture, it's one current loop. If I wanted to be more efficient, I'm going to put a whole bunch of current loops instead of just one. And something is going to turn my current loop. And what turns it? Water going through a hydroelectric dam, a windmill, you could be burning gasoline or the heat from a nuclear reaction or anything like that. It's going to make this thing turn around. And when you do that, you get alternating current. You get AC electricity, this stuff that we plug into the wall down there. And so here's the picture of an actual old hydroelectric dam. This is, if anybody's familiar with it, up north of, I guess, Mission, BC, not the Kelowna Mission, the one north of Abbotsford. There's what they call the powerhouse at Stave Falls, which is in, I think, the early 1920s. It was one of the first hydroelectric dams in BC, and now it's a museum. And so here's a picture inside of it. These are where the coil is that the water is going to be turning. And in front of those, that's where we're going to get the magnetic field. Now, the problem at the time was in the 1920s, where are we going to get really powerful magnets from and put them in the wilderness in BC? Well, they never solved that question. So instead, they built electromagnets. This is a coil that it's getting some power from a diesel generator, and it makes it a little less efficient, but that's how they've done it. And so this is inside at least an old power plant, and they don't let me inside the actual working one beside it. So that's at least one of the significant uses for magnetism. And then we can take a step beyond that and say that if we think about this, we have a changing electric field that's producing an electric current. Now that we have an electric current, that produces a magnetic field from Ampere's law. We now have a changing magnetic field, a changing magnetic flux, that will produce an electrical voltage. And the voltage then produces a changing electric field, which is going to produce a current, and we can keep going around and around and around this loop. And essentially what this is that I'm describing, without trying to put it, is light. Light is a self-sustaining electromagnetic wave. And so these lights and any other lights are producing electromagnetic radiation, and we see it as light. And so a changing electric and magnetic field produces light, and you could do some math. And this was one of the big things that was discovered would have been the early 19th century, that the laws of electricity and magnetism are predicting that pretty much everywhere there should be an electromagnetic wave traveling at the speed of light. So they basically predicted light from electricity and magnetism. Now, often, if you actually were to have a changing electro and magnetic field and you didn't do it carefully, you might get sparks and things like that. Like, think of welding or something like that as an example of changing electric and magnetic fields. You are producing light, but it's not exactly going to be as useful as, say, the lights in this room. And by light, I mean the entire electromagnetic spectrum. This picture is a little hard to read with the chin, but we'll try. I mean more than just visible light. Visible light is this rainbow here in the middle. Over here, there's radio waves. Then there's microwaves, infrared, visible light, ultraviolet light, X-rays, and gamma rays. These are all different electromagnetic waves. We consider them all light. And if we look at the wavelength, the size of the wave, when it gets faster, you're going to get gamma rays and then X-rays and ultraviolet. So when it gets faster, we can think of it that requires more energy to make it go faster. And that might be consistent with what we're kind of familiar with. Gamma rays, probably never been exposed to them, hopefully, but you might be aware that's radiation that could cause cancer. Yes.
When you say faster, it's not the speed that goes faster.
It's not the speed that goes faster, it's the wavelength, so it's the oscillations required to produce it. The speed's the same, the speed's the speed of light. The frequency, well, I actually don't mean, I mean wavelength, not frequency. I guess I mean the period, not the frequency. And so gamma rays will, they'll kill you reasonably quickly. X-rays, you're probably familiar with X-rays. You've been to the dentist or you broke a bone and went to the hospital and they put this lead bib on you and then the X-ray technician leaves the room. So you probably don't want to be exposed to a lot of them, but that's just not going to kill you.
Where do you get a gamma ray?
Where do you get a gamma?
Besides Star Wars.
So there are, well, actually that is one of the correct answers, that they are produced in space. They are produced in radioactive decays. What? Pardon me?
They are used medically.
Well,
I'm not sure, but
there are cases where they use radiation to treat cancer, although generally it's not gamma rays.
So they do use gamma rays.
But generally it's
Yeah,
not.
they got a gamma ray.
Yeah.
They use nuclear material.
Yeah.
My brother had that too.
Yeah.
You don't turn into the hole.
No. And then if we go ultraviolet, well, we know UV light can give you a sunburn and eventually skin cancer. Visible light is not so bad. Infrared. You might be wondering about microwaves. Like, should I be standing in my microwave oven? Probably. It's not a lot of energy, but it absorbs in water and blood and will then heat that up, and I don't especially want to boil my blood. So,
If you stand in front of your microwave to see if your food is cooked.
assuming your microwave is actually a closed, sealed system, nothing happens.
Because it's a longer frequency, the little holes you see there. It's a metal string with little holes. The wavelength of the microwaves are bigger than the size of the holes. So
But sometimes it does interrupt my Wi-Fi.
Then you may not have a perfectly sealed system. Well, no.
Don't fall for that, Renee.
It probably shouldn't. It shouldn't.
Radiation, that is one of the side effects of having radiotherapy for cancers, is that you are then predisposed to more cancers in the future because you've just been shocked with these very
So anyway, the next one is radio waves. And radio waves, if we look at the sizes here, radio waves are about the size of a building. Here's humans, kind of between radio waves and microwaves. Butterfly, pinpoint, protozoas, molecules, atoms, the nuclei of the atoms. So they get smaller and smaller and smaller, the wavelengths, and to get a small wavelength, you have to have more and more energy. And here's what you would see with your eyes if you're bright. If you make ultraviolet light or infrared light bright enough, you can actually see it. And I can claim that I've guess I've seen both at some point. But for the most part, we're seeing the visible light in here. And then the other thing that we can think of is the temperature a body would have to be giving off light of these wavelengths. And so 1 Kelvin, which is 1 degree above absolute zero, we've got microwaves. And then human body would be producing light in the infrared, so they use infrared goggles to try to find people in military applications, and then they get really ridiculously hot as you go out.
Great.
Yes.
Am I remembering correctly again? Snakes can see into the infrared a little way?
I don't know about snakes, but certainly some animals can.
And bees can see into the ultraviolet? Birds too?
Yeah. Well, basically, we've evolved to be able to see approximately the light that comes from the sun, which is mostly the visible light. And not everybody evolves to have exactly the same range that they can see. And different animals will see different. So with that as kind of our background, we have the scientific and pseudoscientific claims that were given. And, well, the first claim, the simplest one, here was the water I was drinking. Will magnets still work underwater? Magnet, it worked before, see? It's picking up all that stuff. Poured some water on it. It still works. That shouldn't be too surprising. Yeah, that's what. Yeah. I actually, when Trump said it was about how something about the submarines in the U.S. Army were using magnets, and he claimed that they wouldn't work underwater if you got them wet. Well, we were actually talking about that in a class the next day, and the comment from one of the students was, only the best get to be the U.S. president.
The man's taken over our discourse. It doesn't matter whether you say something good or bad, it's always got some comparison to Trump in it.
Yeah.
I think the reference was actually to aircraft carriers. Because when they're launching aircraft, they use steam-powered launching systems, and they've now changed to electromagnetic.
I thought there were elevators or something to go between the layers on the submarine, levels on the submarine as well, that are magnetic lifting instead of it's basically a fluid kind of system that was lifting it. So the next one that I sort of want to go to is one on the bottom. Will Wi-Fi and 5G cause cancer? By Wi-Fi, we're thinking of radio waves. And we use radio waves to transmit most information because radio waves don't have much energy. So they're cheap to produce. And the other nice thing is they are very big. So what that means is I'm driving in my car listening to the radio and I drive by another car, it's not going to block the signal. It would if we were, you'd be at least in the shadow of the other car if we were trying to look at visible light. And Wi-Fi and 5G is just the 5th generation cell signals. And so we're talking about radio waves again. Well, radio waves are very low energy. They can't they don't have enough energy to cause cancer. They don't have enough energy to ionize your DNA, which is essentially what would eventually cause cancer. At least there's no direct way that they can do that. You might be able to argue that something indirect is possible. The biggest one that I've ever seen that has some truth to it is you're talking on your cell phone and you always talk on one ear, then the proteins on that side of your brain, if you're talking all the time, might get overactivated and there might be something that happens. That's not really Wi-Fi or 5G causing the cancer. And a simple solution as far as I can is speakerphone or hands-free or something like that. Well, and I think the numbers that they've tried to do that seem to imply that somebody would be speaking on their phone on the same ear for decades and probably with more radiation coming off of it than there would be in real life.
And the thing problem with that take is you go on high-power transmission lines. They do pick up 60 hertz radio waves and stuff like that.
Yeah. But
and then they were correlated those lines with very bad health in the people around this area. They had bad health. Nothing to do with the
yeah,
line.
the explanation that I've heard at least is that the people that tend to live there
are poor.
Yeah,
They
because
live
where would you
lower
live?
property values, lower income, lower everything, and it totally matched. You take any group, same demographics, anywhere without lines, matched perfect with
Yeah.
people standing by the radio lines. And
Yeah.
yet they think it was radio. So what they do is they take chickens and put them in electromagnetic fields, 100,000 times anything like that. Ain't nothing to go wrong with it.
Yeah.
But yeah, it was exactly that. It was just, it's kind of like they're trying to causation and correlation.
Yeah.
People don't understand basic principle.
Yeah.
And that's probably what's going on here.
So then if we talk about
So you could say that poverty causes transmission lines.
Yeah.
Yeah.
Where are the ports people? That's where we're going to run our transmission line.
So then we can talk about how magnetic therapy can cure diseases like arthritis. Some people have their bracelets. Yeah.
We've got a job, he quit his job, and he's selling those magnetic bracelets. All the rage.
Yeah.
And all.
So there are three explanations which have a kernel of truth but are wrong for how they would work. I mean, the first thing is that if you actually had a magnet here, say on your wrist, what I would expect is there's iron in your blood and hemoglobin. It could be attracted to it. Okay, that's going to force your blood to move, I guess. It's going to force your blood to move to here where where it is. And then if there really was a strong enough force of attraction, you'd get a whole bunch of blood to coagulate there and you get a blood clot. And that wouldn't be any good. So really, if you actually started to do some calculations and say, how big a magnetic field do I need to have any considerable amount of iron, considering that your blood isn't pure iron, it's some compounds that have some iron in them, but there's a lot of other stuff. You probably would have to be in some of the largest magnetic fields that man has ever generated. We don't have problems when you go for an MRI imaging that your blood all clots in some position. So it would be even larger than that. So you'd have to be traveling around with a magnet that's cooled probably by liquid helium. This would not be something that's reasonable, that's not that people could do. So then the second argument somebody would use is, yeah, but what about the Lorentz force? What about this force? That's going to cause things to move in some unpredictable direction. The problem is they can't move in an unpredictable direction. Your blood is confined to capillaries and veins that it's in, so it can't suddenly flow in some third direction. So that's impossible, and that's also would require a huge magnetic field, a huge charge to be moving very quickly. So the third answer, somebody then comes and says, oh, what about Faraday? You can generate an electric current if you have some sort of molecule going by in your blood that has some sort of path that a current can go through. The first question is, well, what is that molecule? And the answer is, I don't know. I don't think there is one. And then the next question, would be, okay, so you have this one molecule that comes along, it's going through your bracelet, and I guess as it gets to a higher magnetic field, the flux is going to change a little bit. It's going to produce a tiny, tiny current. In order for this to be significant, for any of this to be significant, you need a huge, huge magnetic field. Nothing that could happen by, nothing that you could carry around. If you had a bracelet that had that big a magnetic field, you'd have problems like all of a sudden the hammer comes flying towards your but I can actually tell you that, I mean, off topic from that, it was mostly when I was working on my PhD, but periodically I seem to erase my bank card and have to go get a new one. That does happen from working around magnetic fields.
What about the magnetic mattresses? Think it's stronger?
I mean, the fact that it's bigger means there's a magnetic field sort of more or less everywhere on your body, but no, you're not going to have a big enough magnetic field. It's not, your mattress doesn't, your keys don't stick to the mattress, do they? If you have a hammer, it doesn't come flying across the room and stick to the mattress.
Well, and the other thing too is, why would you want to have your blood drawn to a specific place?
Well, yeah, I assume if it were to make sense, I have arthritis in my wrist, therefore I have a bracelet around my wrist. But if I also have arthritis in my shoulder, I don't know.
It's homeopathy. They
Yeah.
have a reason behind it, but there's no reason. It's just magic. They try to tie in scientific words.
There's a to all of this is a kernel of truth, but no more than the kernel.
Would that at least help circulation? No.
No, not in any meaningful way.
Circulation does this.
Circulation, you want to have things move, and you want to have the blood move, and if it's just being held in one place by the magnet, it's not moving.
And the movement of blood has nothing to do with arthritis.
No, yeah.
I mean, you want to have an increase in fluid between joints, but that's not blood. That's synovial fluid, which is
You also have to have the current from the rebels so damned in one bed.
Something like that. Yes. You would need some. That is the case. You need something. You need some ridiculous magnetic field that would be completely unsafe.
You should YouTube everybody. YouTube the floating frog. Where you put a frog in a massive magnetic living frog. Put in a massive magnetic field and it's floating.
Yeah.
Spin around floating like.
Yeah.
Gravity's on. You just put it in there, and there's no metal in it or anything they done to the frog. It's just regular iron and salt in his blood, and boom, he's up floating around.
Well, the best explanation is the frog is largely diamagnetic atoms, which have a weak repulsion. But if you have a big enough magnetic field in all the directions, you can have repulsion of the frog in all directions. Yeah. Yeah.
So, Greg, as we know, we live on a flat Earth, right?
Okay.
Which is the North and the South Poles?
Uh-huh.
Which argument do we use against flat Earthers?
Actually, the most meaningful argument for flat Earth has nothing to do with magnetism. The fact that when there's an eclipse, the shadow of the Earth is always round. What other shape can always be round, no matter which size you're looking at? So I guess the next question here is, would putting a magnet on your skin pull metals from your body? Not in any meaningful way, not unless you have a ridiculously high magnetic field, which you don't want to deal with. An MRI can't do it. But an MRI can't do it. It's not going to pull metals out of your body while you're in the MRI.
What is an MRI doing then?
That's actually the next slide when I get to an MRI. Okay. And
If a magnet could pull metals through your skin, it'd be an absolutely fabulous way to remove shrapnel from people who had.
I think it would be very painful. I think it would be very painful to have things pulled through your skin.
Your skin, but it goes through your spine first.
Yeah.
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 When they first started,
Yeah.
with, these different scans, like CT scanners and all that, they discovered that, metal is pulled out by the magnet and it just goes through whatever. Be that your brain, your
Yeah.
heart, your lungs.
Yeah. So then the question, can wearing magnets protect you from EMFs or 5G? In principle, the idea makes a little bit of sense, except for a couple problems where it doesn't. What this would be, this is the Lorentz force we'd be talking about. That you have the light is an electromagnet, and it's in the magnetic field is going to move it in some direction. The question is which way is the some direction. If you had a big enough magnetic field, and this isn't as big a magnetic field as the other cases, this might be something I could build an electromagnet that would have a big enough magnetic field. What's going to happen if the light is, say, going this way, you've got the electric vector in some direction. It could be, who knows, but it's perpendicular to the direction that it's traveling. So it might be going this way, it might be going that way, and the magnetic field is the third direction perpendicular to that. So I don't know which direction the magnetic field is going in the light that's coming toward me. So in principle, the Lorentz force would be enough to deflect the light. It might deflect it toward your heart or toward your brain or something you're worried about. It might deflect it away from you. If we polarize the light, which really means we're making all the magnetic field vectors go in the same direction, polarizing sunglasses will do that. They block all but the whatever direction you have. Then you'd at least be able to predict which direction it would go. It wouldn't be a very big deflection with any magnet that you could wear. Students at Brandon University in the upper level lab and some of my research, I do use this as an idea, though, that if you send light through a big magnetic field, you can deflect it. And this deflection's not easy to measure. It's a small deflection, but you can measure the deflection if you're careful. And by a large magnetic field, we have a water-cooled electromagnet that it would be going through.
That's the big problem, though, when you say in principle, when you're saying stuff like that. That's under extreme application in a scientific environment.
Yeah.
So you're being honest, it's in principle. That is food and fodder for the woo-woo crowd. Because if any science is grabbed onto anything like that,
yeah, but what I'm basically saying is that yes, we can bend light. I've done it. No, here you're not going to be able to bend it by a big enough amount that it's going to miss your body when it otherwise was going to hit you or something like that. And if you don't know the polarization of the light, you don't even know which direction you're going to be bending it.
You don't care
and but that is why the Earth's magnetic field deflects the magnetic ions that are coming off the sun, the electrons and protons and whatnot, that are the solar wind, and then they gather at the north and south poles, and then they form the auroras, and we can see them. Yeah, we're protected from those that come from the sun, from the Earth's magnetic field.
So is that why light bends when it goes around the planet?
Gravity is the reason. That's gravity.
Right. All right.
Yeah.
I'm getting things mixed up.
Yeah. And so the final question, we sort of talked about it. Will the Earth's magnetic field flip overnight and cause global disasters? I can't say no. But I probably its flip will take hundreds of years and go from one direction over to the other direction in the hundreds of years, and we may even be doing that right now. But there are simulations that show that it is possible to zero out and then reappear in the other direction in a day or a few days anyway. Nobody's observed any of this. And then the question is, would that cause global disasters? I think it would be as big a problem as Y2K. The big thing is you do use the magnetic field direction for figuring out their location. And yeah, and so do fish and birds and whatever. And it very well could mean that the salmon run that year gets lost. But it probably doesn't mean that every plane's going to fall out of the sky any more than that happened in the year 2000.
Well, we have GPS now, so.
Yeah. 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 So the final thing I wanted to bring in here is MRI, magnetic resonance imaging, or its original name, NMR, nuclear magnetic resonance. And they dropped the nuclear because that scared people. But it's exactly the same. So here's the person gets put inside the magnetic coil here. And essentially what's happening is I can give you you think of it as an AC magnetic field. It's a magnetic field that's varying with time, and it's going to absorb into the subatomic particles in your body if they are rotating at the same frequency as that magnetic field. And what frequency do they process depends on their surroundings. So if I'm in a muscle cell, I'm going to process at a certain speed. If I'm in a fat cell, if I'm in the brain, if I'm in a cancer cell, I'm going to process at different speeds. So or different frequencies, I guess. So I can then non-invasively say that, oh, this part of your body is processing at the speed that is a cancer cell. Therefore, you have cancer there. Or I can say that this part of your knee ligament is missing because there's no muscle cell that's processing at that point in your knee. And so I can get images like that. And the nice thing, at least the way physics thinks about it, is MRI, NMR. This was something that was developed, I guess, by somebody like me who doesn't know anything much about medicine, but knows about magnetism, and yet it has a big advantage to medicine in that you're able to see things that you otherwise wouldn't be able to see. And it's not only medical. We call it an NMR system, but it's an MRI system that's in one of the labs at Brandon University, and chemists generally are using it to figure out exactly which molecule did I just make in my reaction. And I've even seen situations where people have done MRI imaging on vegetables and things. So, I guess with that, we can conclude that, physics is fun, is the first thing. And I'll read what this was supposed to say so it didn't come across properly. Because this is a cartoon I actually put on all web pages for my classes. This guy's shirt says, physics is fun, and their PHs like this. And he crossed out the PHs and wrote in Fs. And hey, just because adults in the physics department can't spell doesn't mean I have to go around looking like an imbecile. So, any questions? Yes.
Is an electromagnetic pulse, like, is that real? Is that
That's just a
weapon?
yes. That would just be a huge, basically a huge flash of light. That would be enough that because it's got a high electric field, high magnetic field, it would damage the electronics in whatever region.
Would it damage people?
Most likely it would damage the electronics. Would it damage people? Probably it could cause cancer or something, but it wouldn't damage people in that they would know immediately.
Americans did it already. South Pacific in the 1960s, they blew one up in up in the atmosphere, about 1,000 miles away from Hawaii, and it really did a lot of damage. It fried their electrical systems in Hawaii over 1,000. They didn't even think it was going to happen.
Yeah.
I think it was called Star Shot or something like that, or one of the names of the nuclear thing, but they blew it off, and they kind of said, "Ooh, we don't need to vaporize this. You could bring the world into the Stone Age with a couple thousand nuclear weapons in space."
Mhm.
So satellites would be gone, everything would be gone.
Not just hitting visible light, though.
It's not visible. That wouldn't be necessarily visible light.
So it wasn't so much the light; it was the, like you said, the intense magnetic field, electrical field. It's like having our own aurora borealis, Alice, or like the mass, the energy, the charge of all the.
The very largest magnetic fields, and there's a high magnetic field lab in Florida, up in the Panhandle where nobody lives. I don't know exactly, Pensacola or something. They are actually what they call explosive magnets. The idea is that when you've got them turned on, there's so big a magnetic field that the North and the South poles blow apart from one another. And so you have to take your data very quickly and be able to survive the explosion somehow, which is done. Yeah, actually, when I finished my PhD, I wound up going to Argonne National Lab outside Chicago, but that was the other place I interviewed. And I didn't get that one.
So probably from mankind's point of view, an MRI was probably a huge benefit to civilization. What's next to come? Going from the lab to practical applications, what do you see as being the next big?
The easy answer to that is to say artificial intelligence and things related. I mean, if you no, they don't.
Oh,
They don't. In terms of magnets, the big thing, magnetic refrigeration. That's actually something I worked on at the University of Victoria. That is something. I would say the answer before that might be magnetic recording in computers, which is used, but generally by the military. The idea you have your magnet, it's magnetized this way, it's a 0. If it's magnetized that way, it's a 1. If it's magnetized in any other direction, it's broken. And this means that you instantly can boot things up because all the information is stored even with no power in it. And satellites and things like that are using magnetic recording, but in some military applications. But it is possible that there would be an instant boot computer because the information is stored magnetically.
Would these magnets be like you're talking about atomic size magnet?
I'd probably be talking.
They had like magnetic rope core memory, like in the 60s.
Yeah,
Like
but I'd probably be talking about
molecule size.
not molecule size, but tens or 100 atoms or something like that per bit.
Atomic size.
In what material?
The best answer that they use is something called permalloy, which is a nickel iron alloy. When you get as small as that, you don't care about the fact anymore that it's a soft magnetic material, because soft magnetic materials, I've sort of quickly said that they lose their magnetization. They don't exactly. They break up into microscopic domains that keep their magnetization in just random directions to them. So macroscopically, there's no magnetic field, but there really are domains that hold on to the magnetization, and we can use those domains to store the information. And the permalloy is great because if made properly, it does not have a preferred direction that it wants to be magnetized in, unlike most other crystalline materials. The crystal structure says that I want it in this direction, but maybe we don't actually want to store it in that direction.
So it would be permanent until you.
Well, permanent is not permanent because it's kept probably at room temperature. Thermal vibrations would eventually be enough that you would start to lose some of the information. the sort of joke thing that people have, I think they've done, at least they've suggested, is what they call the Arizona mailbox test. In the summer, you put this thing in the mailbox in Arizona and leave it there and see how long it lasts. I mean, you can simulate that without actually going to Arizona.
So it'll be faster than solid state
Yeah.
hard drive?
Yes. Yes.
Really? I'm like thinking about the old VHS tapes and stuff. Like I know.
Yeah.
When
They
tapes
were
are
magnetic
fired,
tapes.
physically change direction, or is the polarity of the magnetism in the filing or the magnetic material, is it physically?
Yes, the magnetic material physically switches direction,
Yeah.
and you get this region's up, the next one beside it's down, and up and down, and so on. And there's a recording head that travels by and can read them all.
So, but this new magnetic would be like the actual same principle. You physically changing it.
Yeah, it would be the same. It's the same principle for the most part, with a bunch of other technological changes that are required.
It was so easy, it would have been done already.
Yeah. I mean, the biggest difference is that, so on your tape in the VHS or whatever, you would either be magnetization, I guess it would be to the left or to the right. But if we pointed them either in or out, you can get better density. And then when they're in or out, you kind of have a sandwich where you have the non-magnetic material or the magnetic material and another non-magnetic material. And you can read them from the resistance going through them, that if I put in a spin polarized current that's in the same direction as the magnetization, it's going to tend to be a much higher amount of current that gets through than the other way around. So this becomes a resistance measurement, which is much simpler than trying to measure a magnetic field.
How far along is that?
They are doing it in some military applications. I don't know exact. IBM was very close in the early 2000s. They sold it off to Hitachi, and Hitachi's the main company doing that. I know IBM people who referred to it as the Hitachi IBM venture, and the letters that were HIV were chosen on purpose because I don't think they were too happy with how that was run.
Any more questions? Well, thank you, Greg.
Okay.
We had a member of this group many, many years ago that